So now we're going to talk about radioactive decay. Okay, and we're just going to briefly discuss the types of radioactive decay and where you will find these types of decay. All right, so there's four basic processes. Okay, um, first of all, there's alpha decay, and the alpha decay, beta decay, and gamma decay were basically discovered kind of in order. And they didn't know, the discoverers didn't know what was going on. The researchers who found these did not know exactly what was going on. All they knew was that something was going on, and so they just named them in order of discovery: alpha, beta, and gamma. It turns out that alpha decay is when a helium nucleus is released. Beta decay is when an electron is released. Gamma radiation is when a photon is released. And the fourth is neutron radiation. And this is when a neutron is released, or multiple neutrons. Okay. So these are the four types of radioactive decay. And the first question we want to ask is, why do nuclei decay? So, nuclei decay, the simple answer for why do nuclei decay lies in energy. Okay? If a nucleus is too energetic, then this can lead to an unstable nucleus. And there are a few different reasons that a nucleus can be unstable. We're not going to explore all of them in any sort of detail, all right? But the root of the issue is that a nucleus contains too much energy. When it contains too much energy, it wants to go to its naturally lowest energy state, and it wants to release some of that energy to get there. So, first things first, let's talk about alpha decay since it's the first one on our list. And for example, okay, for example, what we have is one situation where alpha decay occurs, all right, is in uranium. Okay, in the decay of uranium. Now, there are several different types of uranium. Uranium comes in several what we call isotopes. Okay, uranium comes in several different isotopes. Now, remember that the mass number represents the total number of nuclear particles. Sometimes these are called nuclides. And these make up or are comprised of protons and neutrons. Right? The atomic number is the total number of protons. Okay? Now, the atomic number, this is what defines the element. So, for example, uranium has an atomic number of 92. Okay? So all uranium atoms have an atomic number of 92. So all uranium atoms will have 92 protons. One specific isotope of uranium will contain a total of 238 nuclear particles. Okay? So this is one isotope. So the number of neutrons for a given nuclear situation is the mass number minus the atomic number. Okay? So the mass number minus the atomic number. And so in this case, in this isotope, there would be 146 neutrons. Okay? Another isotope of uranium is U-235. And it still has 92 protons. And so U-235 is another isotope. And in this case, it would have 143 neutrons. Okay? So when we talk about atoms, we're usually talking about a specific isotope, right? And we usually refer to the mass number, okay? So when we say uranium-238, the 238 would be the mass number, the total number of nuclear particles, or uranium-235, 235 being the total number of atomic particles, or nuclear particles. So, alpha decay, all right? One situation of alpha decay. And remember that alpha decay, okay, is a helium nucleus. And a helium nucleus contains 2 neutrons and 2 protons. So it contains 4 nuclear particles and 2 protons. 2 of those are protons. Okay? Keep that in the back of your mind. So one U-238 is highly radioactive. Okay? U-238 is highly radioactive, and what happens with uranium-238 when it undergoes a decay transition, uranium-238, the nucleus of uranium-238, okay, so there are 238 nuclear particles here, and the decay products are an atom with 234, since we lose 4, and then we have the 4, okay? And not only that, but because this is a helium nucleus, let me make that a little bit better. Because this is a helium nucleus with 2 protons and 4 nuclear particles, that means that if this is uranium with 92 protons, I'm losing 2 of those protons to the helium nucleus, so this has to be the element 90. And it turns out that element 90 has the symbol TH, right? And we started with U-238, but I lose 4 total particles, so now I have 234. So this is called the parent, this is called the daughter, okay? and this is sometimes called the product, right? But this is not as important because this is going to be the same in each alpha decay situation. What we're really concerned with is what's going to happen to the parent and what type of daughter does it become, right? So anytime you have an alpha decay, you lose 4 from your mass number and lose 2 protons, or lose 2 from your atomic number. So this is a genuinely different atom, okay? TH234 is fundamentally different than U238, right? So they have different chemical properties. These are 2 different actual elements. And alpha decay and beta decay, this is true. With gamma decay, gamma radiation, that's not necessarily the case, right? So let's move on to beta decay. And with beta decay, right, what happens is an electron is released. And what the process here is, you have a neutron, but a neutron is neutral and it's a little bit more massive than a proton. So a neutron, in some ways, is made up of a proton bound with an electron, if you squeeze a proton and an electron close enough together, you can get a neutron. So you can think of a neutron as a proton bound with an electron plus the binding energy to keep those 2 together. Okay? So this is where a neutron's mass comes from, is the mass of the proton, the mass of the electron, and the binding energy that it takes to keep those together. Sometimes a neutron will decay, and the neutron will decay to a proton plus an electron. Okay? So in beta decay, it's this electron that gets expelled from the nucleus. So you have let's actually write an equation down. So one process where we observe this is in cesium, and cesium becomes barium. Or another, actually, let's start here. Let's start with sodium and neon, right? So we can start with sodium, and sometimes a sodium atom will decay, and we will get neon Now, what's happening in this equation, okay? What's happening in this equation, when a pure electron is released, you go down, you go up in atomic number because you're gaining a proton. But sometimes, instead of an electron that's released, you can release a positron, which is the antimatter equivalent of the electron. And when you emit a positron, you're actually losing positive charge from the nucleus, and so your atomic number will go down. Okay? So we do actually need to be very precise about this. A situation where an electron is actually emitted is the cesium to the barium. And actually, I really should write these are atomic numbers, not mass numbers. So this should be 11 here and a 10 here, right? But if you have cesium-137, okay, this can decay into barium-137 plus an electron, right? So barium is one space higher on the periodic table okay, one more proton than your cesium. And again, this is because we're losing a negative charge, therefore we're gaining a positive charge, right? We're losing a negative charge, so we're gaining a positive charge. And therefore we will move up in the periodic table. Okay? So that's beta decay. What this would look like, all right, is I'm just going to draw a few particles here. I'm not going to draw the whole thing. But suppose we have a few protons and some neutrons, and this neutron here decays, right? So it expels out your electron, and we're left with a proton, a neutron, but one more proton. Okay? So, that is beta decay. And then gamma decay Gamma decay is unique because it does not change the atomic number. And in fact, it doesn't change any number. Okay? All that gamma decay does, not sure. Okay. So all that gamma decay does is release excess energy. And it causes a nucleus. I'm not even going to give these protons and neutron designations. I'm just going to say, imagine that this atom is highly energetic. This nucleus is highly energetic, right? It's shaking, it's wobbling. It can release a gamma photon and it will settle down into a lower energy state. Okay. And so, when this occurs, you have basically just an atom that's de-exciting, okay? And you're gaining some radiation, but that's it, right? So there's nothing going on here that's changing any of your values, right? So those are the three types of radiation. And I do want to stress one thing, okay? So we'll actually put it down here. And that is that radiation, radioactive processes, are random by individual atoms it's statistical for a group. And what we mean by that is, if I have a collection of atoms, now these are not nucleons, these are going to be individual atoms. Suppose I have a collection of atoms, and these are atoms that are potentially, say, susceptible to beta decay. Just throwing it out there, right? If these atoms are susceptible to beta decay, what goes on is I cannot pinpoint any one atom that's going to decay at a given time. I will not know if or when, say for example, this particular atom is going to decay. I have no idea. Okay, I cannot predict any one individual atom, whether it will decay, and if it does, when. However, usually samples, even small samples of material, contain millions, if not billions or more, of individual atoms. And as a result, when you have that many atoms, statistics are very, very good. And you can say that on average, an X percentage, or some percentage of the sample will decay in a given time. You can't state which individual atom is going to do it, but you can state that so many atoms will, right? So that's what we mean by statistical, and that gives rise to the idea of the half-life. Now, the half-life deserves its own video, so we'll do a short one in the next segment, but just be aware that the half-life is based purely on statistics, okay? Based purely on statistical probability. And the half-life, by definition, is the amount of time it takes for a sample to, or for half of the parent atoms to decay into daughter atoms in a given amount of time. Okay. Let me say that one more time. I don't know that I was terribly clear. The half-life is the amount of time that it takes for half of a sample of parent atoms to decay into daughter atoms. So if I start with a population of parent atoms and I let them go through their decay processes, when half of the parent atoms have decayed, that is the half-life. And for most radioactive elements, we know what these half-lives are very, very well. So this gives rise to things like radioactive dating. If you have a sample of material with a substantial amount of radioactive substance, you can radioactively date what the age of that substance is because of this idea of the half-life and its statistical probability. Now, it can be very difficult to do, but in principle, the statistics are very, very simple. Okay? So, that is a bit about radiation. We don't really talk about neutron decay. Basically, neutrons can also be expelled from nuclei. Okay? From rather large nuclei where there's, maybe 100 or 200 neutrons, sometimes one of those will get sent out, and the mass number of the atom will change, but not the atomic number. Okay? But that's not as important for our purposes as the alpha, beta, and gamma decay are. All right? So, we will see you next time.